Okay, so we have seen this micron rules now. Okay, now the other rule, layout design rule is called as lambda design rules or simply lambda rules, right? So as opposed to micron rules where we had all the dimensions in absolute numbers, okay, but here we specify a parameter. Okay, let's say the parameter is lambda. Okay, and all the dimensions will be in terms of lambda, right? So it may be 1 lambda, 2 lambda, 3 lambda, 4 lambda, 5, 6, 6.5, 7, whatever. Okay, so all the parameters, all the distances, all the dimensions, length, width will be some multiple of lambda. Okay, and lambda will be the smallest quantity, obviously. So it will be having some value. Okay, it will be having some value. So let's say if lambda is suppose 1 nanometer, and some distance is coming out of with some, let's say 6 nanometer. Okay, some required distance is 6 nanometer, so, or some required separation is 6 nanometer. Okay, then that will not be written as 6 nanometer, but rather it will be written as in terms of lambda it will become 6 lambda. Okay, so all the dimensions, all the spacings, all the metal widths, uh, all the line widths, the area, the dimensions of the active region, and all those things will be specified in terms of a single parameter, and we call this parameter as a simple lambda, and hence it is called as lambda rules. Okay, so lambda rules which specify the layout constraints in terms of a single parameter. Okay, single parameter, it's written x here. It can be, it's a simple variable, so it can be uh, generally it's called as lambda. Generally it's the notation is lambda. Okay, but it may be anything because it's a variable, and anyhow it's a variable. Okay, so it's just a matter of understanding, and thus allow linear proportional scaling of all geometrical constraints. Okay, so one advantage of this lambda rules over micron rules is that all the dimensions in the case of lambda rules will be uh, proportional to some multiple, proportional to lambda, and all the dimensions will be some multiple, simple multiples of lambda, and hence they will be all the dimensions will be having some relation to each other, and that relation would be a simple linear relation. Okay, and the dimensions are easily identifiable, easily describable, and it's easy to design the layout circuit when it is being designed with the help of lambda design rules. Okay, and it is generally used in the academic section. It is generally used in the academic section for learning and teaching purpose. Okay, so generally because this is a bit simpler to design with, to work with, so students are taught with the lambda design rules, and the design are being performed by using these set of rules. Okay, and this micron rules, okay, this is generally used in the industry, and where all the dimensions are in actual numbers. So you may have all kind of numbers. We may have, suppose some distance is 1 nanometer, some distance is 1.2 nanometer, some distance may be 6.15 nanometer, some distance may be, let's say, 4.8 nanometer. Okay, so there is not no boundation that it should be a simple multiple of something. It can be anything, it can be any number. Okay, and generally it is also specified up to some, like let's say 1 or 2 decimal places. Okay, after the decimal point, so it becomes complex in nature, and it is also at the same time it is very hard to design. It's a bit hard to design with, to work with micron rules, because every other dimension is not expressed in terms of some parameter, but it's a simple absolute number, so it's very hard to design, to remember those things. Okay, but here in case of lambda rules, some things may be remembered, because all in all we will have some many terms which will be sharing the same multiple of lambda. So it becomes a bit easier to work with lambda rules. Okay, so look at this figure illustrates some of the typical MOSIS layout design rules. MOSIS is think MOS implementation system. Okay, MOS implementation system. So there are various design rules, layout design rules specified by various types of various kinds of organizations. Okay, one of the popular is MOSIS design layout design rules. So let's have a look that how does it tries to define. So active area rules, suppose it is called as R1. So what does R1 specifies? R1 is the minimum active area width, the minimum width of the active area. Active area is that area which where the diffusion is done, and in that area the transistor will be formed. Okay, and this R1 should be at least 3 lambda. Lambda will be having some parameter, will be having some value. Okay, that value is fixed for a particular process. Okay, and this becomes 3 into lambda, right? So ultimately this will also come in some sort of number. Okay, but that will be simple multiple of lambda. Okay, let's see what it is. R1. Okay, so I have inserted one example also. This is a simple circuit layout circuit, and let's say this active area is described by this rectangular area and R1. Okay, look at this, the R1. Okay, I think this is the active area, and this is extending like this, coming here, here. This all is representing the active area. Okay, and it is talking about this this dimension, this R1. So what it is? It is the minimum active area width. Okay, so this width should be 3 lambda, at least 3 lambda. It cannot be less than 3 lambda. Okay, it can be more than 3 lambda, it's okay, but it should be at least 3 lambda in width. Okay, now we go to R2. R2 is the minimum active area spacing. This again is 3 lambda minimum. Okay, so keep pay attention that this is the term minimum. Okay, so R2, right? R2 definition was active area spacing. Okay, so where is R2? This one. Okay, this is one active area, this is one active area, this rectangle. Okay, and this is another active area. Okay, and the spacing between any two active areas should be at least R2. This is what it is specifying. Look at the distance between this active area and this active area should be R2, that is again 3 lambda. Okay, so similarly there are rules for every other kind of material that's used, or every other kind of shape and structures that are used. This is polysilicon rules. R3 minimum poly width should be 2 lambda. Okay, so let's try to find out R3. Where is R3 minimum poly width? R3 is, okay, this, look at this, this is the polysilicon structure like this, some graded rectangular shape. So this is the polysilicon material. Okay, and the minimum width of this polysilicon material should be R3. Okay, 3 lambda, I think, no, sorry, 2 lambda, right? So similarly you can relate all of these parameters with this diagram, and look at every other dimension is being described with the some dimension. We have R1, R2, R3 up to R 13, 10, then 15, 16, 18. So there may be many dimensions. Okay, the dimensions in terms of the width and length of a particular region, the dimensions in terms of the spacing between the two types of regions, or spacing between the two different types of regions, these kind of things. Okay, so we have some metal rules also. So this will define R8, let's say the name, minimum metal width 3 lambda. So minimum metal width is R8 3 lambda. Metal is represented by this thick lined thick border rectangular area R8. Okay, this is R8, so this should be at least 3 lambda. This is the metal line, this is the metal area. Okay, this whole is the metal line, and it is talking about the minimum width of this metal. So this should be R8 at least 3 lambda. So there are some contact rules. Contact means the contacts which are fabricated for taking out the connection to the outer world. Okay, so let's for example look at it. R15 active contact size should be at least 2 lambda. R15, so where is R15? This one, R15, this is what? Active contact size 2 lambda. So this will be 2 lambda, 2 lambda, 2 lambda by 2 lambda square. Okay, so this is 2 lambda and this is 2 lambda. Since this is square, so all the dimensions, all the sides will be equal. Okay, so these are contacts. This is a contact, this is a contact. Look at here, this is the notation for contact. So similarly this is the contact. Okay, this is the contact, this is the contact, like that. Okay, this one 6 lambda, the biggest dimension present here in this slide. Minimum active contact spacing R20, minimum active contact spacing on different active regions. Okay, R20, R20, where is R20? So they are present on different active regions. Okay, so this contact is in this region, this active area. Okay, this circle, this square, this rectangle. Okay, and this one, this R15, this contact is within this active area. So this R15, so this contact is present in a different active region, and this contact is present in a different active region. So what should be the minimum distance between these two types of contacts? R20 should be at least 6 lambda. Okay, so why are these important is that because these are designed by with the experience it comes to the engineers, to the designers, to the fabrication engineers, and the data collected from history that will help those engineers to fabricate, to formulate these rules, so that when actually these rules are followed, there would be very less chance of fault occurring in the actual fabrication of IC when it actually goes through the process. Okay, but we can also design an IC by not satisfying these rules. Okay, this is not it is advisable to follow these rules, but some IC may be designed without following these rules. Okay, so you may actually take it as we may not satisfy this 2 lambda. Okay, you may go like 1.5 lambda. You may also design it with by taking 1 lambda. You may take this parameter as, let's say, 2 lambda. Okay, this not 6 lambda. You may take this as 3 lambda. So if such a design is such a circuit is designed which will not actually follow the layout design rules, then there are pretty high chances of getting that chip malfunctioned after fabrication. Okay, there will be no guarantee given by the fabricators that okay, if they fabricate it, then that chip will work or not. Okay, so this is the minimum thing. Okay, these dimensions should be followed. Okay, why they should be followed? They should be followed in order to get the optimum, in order to get some kind of confidence that okay, after following these these layout design rules, then we can expect that the chip will function, the chip will come out with proper functioning. Okay, it will not contain those kind of errors which are usually appearing when we don't follow the layout design rules. Okay, so this will like these things will give some sort of guarantee, some sort of confidence that okay, the chip will come out with proper functioning. Okay, and that is why these rules are designed. So uh, whenever a physical design is being done by a VLSI engineer, design engineer, physical design engineer, he or she will always try to look up at some sort of layout design rules. Okay, and it's a very good practice to always look at those design rules and try to follow those things. Okay, so I think with this your module 1 is over, and from next class I will start module 2 portion. Okay, module 2 for VLSI design, and I will start with the MOS structure, metal oxide semiconductor structure. Okay, so module 1 is over here, right? Okay.